this is joint work with Eugen Gorski and Matt Hogenkamp. And this is a plan with some motivation and motivification, infinity exercises, more kind of details of the construction. And so there's some maybe something about SL2s. Yes, SL2s. So what is the motivation? Let me start with construction of the complete polynomial. So you have a link and you write it as a closed, and you write as a product of some generators. So you like 1 plus 2 or minus 1. And then you use this thing called the Hecke algebra. So let's say M is a yes. And then there is this Hecke algebra. And you know it's generated by 1 minus 1, and the relations are so okay. The one is sort of like this, and then braid relation. Quadratic relation, which I like to write something like this. Yeah, so what you have to do to obtain complete polynomial, you have to first send your braid to this Hecke algebra. So you take sigma I beta by Ci, you obtain. Also call it beta because so beta in the Hecke algebra. Then you want to, and then you want to get some polynomial. So you start with the trace. So this is trace on trace 0. Let's start with trace 0, and the Hecke algebra is defined by taking the any element. You write it. Hn has a basis of n factorial element. W is the permutation. And then you take the trace 0. C0, C1, the coefficient of the identity. And then the conflict. You use this trace, but you can modify it by any central element to get another trace. And you do as follows: put here a product of 1 minus a I n times and ji is just Murphy. So it's sigma I minus 1, sigma 1. That's it. So yeah. Now I want to bring up some other. So there is this other point of view on Hecke algebra, which you can try to use to get something more interesting. So another approach to the Hecke algebra is that okay, that was not very efficient. So I can move another approach to the Hecke algebra. you take the finite group n over q. This is the finite field with element of q, for instance. And then you have here the group of regular matrices, and then you look at the double cosets. Like this, and it is natural from such a situation to construct R. So you will take the vector space with bases given by this double cosets. It has an algebra structure as a algebra, and the text turns out to be actually exact Hecke algebra. So it equals. But something interesting happens here. Q is a number, but there Q is a parameter. But it turns out that all the relations in algebra depend polynomially on Q. Right, and then what you can do with this and this trace. So let's say at least for Q equals for A equals 0. Equals 0 corresponds just to the term 0. So in the case of 0, and if is positive, only positive powers appear. You can interpret the Homology as follows. You A equals 0 equals to the number of tuples of complete flags in F. And so you consider flags of vector spaces. And so you have this flags F1, L. And you such that Fi and Fi plus 1 are in a relative position sigma I. So sigma, sorry, for this. So this is corresponding. So the number is the number of generators in my braid. You write beta as sigma, and the sigmas themselves correspond to pairs of flags. And what it means is basically just that the flags are the same. So there are n steps in the flag. They are the same everywhere except the step given by this generator. So what is important here is that the Homology polynomial at A equals 0 is interpreted as a number of points, number of some things over finite field. Okay, and now so this is the motivation now part. Excuse me for being. So there is this idea coming from number theory. Let me try to explain it. So you study some. So what is motive? Let's say just take any system of polynomial equation. So the motive, let's say, is system of equations and some variables like P1, P0, P2, and so on. And then in number theory, you associate to such a thing, you can associate many things. One thing you can do is you can count the solutions over a finite field. And this will gives you a number. So it gives you an integer number. And or in some cases, if the number depends nicely on Q, maybe get a polynomial. It depends on the number. Or you can do some other things. You can take homology. And that gives you some vectors. You can get, you can integrate something. And let's give you some else and delta nodes. So, so in number theory, you sort of try to, whenever you see something on the right, you kind of think about some kind of motive hidden behind it. And then you should think about its different realization. So this, and that's clearly we should bring into this this picture, because we have some numbers which are counting points on some space over a finite field, and by doing other operations to that space, we can try to get some other interesting, hopefully interesting invariants. So the idea is that for a link L, you should associate some algebraic variety. And then by doing things like you can say, let's say, take cohomology, you should get Havana homology. Or you can do other things like what else? If you want to get a category, you can consider the category of some coherent sheaves, for instance. Category of coherent sheaves, we use some category. And or you do some kind of matrix factorizations on that variety. And that sort of, this is our organizing point of view. So, and this arrow should be called motivification. Okay. Motivified link invariant. Okay, so right, that's a very now what is the what do we want? So how do we apply this picture?
I have a question. Up to what do you see the algebraic variety? Or do you expect it to be invariant up to bilateral transformation up to what?
It's, okay, that is not very. Yeah. Okay. In some cases, there is some variety that you know it's like that variety is the right one. But if you want, you can cook up some strange examples where you don't know. But one as a first approximation, you can take a variety whose points are the tuples of flux. So okay, so what in this talk, so this was the first part of the information. Second, so more details. So I was studying some character varieties. And that's how, so you take some Riemann surface and character variety parameterizes representations of the fundamental group. So this is my surface. Well, and let's say from 1 to G and 1 of C. And So this X is up to conjugation. And there is some interesting structures you see you have on there. So it turns out X is always a symplectic, homomorphic symplectic variety. And so you have the cohomology of X, and it has a class of this symplectic form, for instance. But also there are some higher tautological classes. And they are obtained by basically, so these differential forms are obtained by, for instance, triangulate your surface. And each triangle, and then put some cocycle and somehow add them up together and you get some closed differential form. I don't need the details here. I just want to have some approximation. And then, and the idea is to think about these varieties that we had about with flags. It's somehow similar to these braid varieties. So for our braid varieties, about the flags, the one I mentioned before. So you should think about it. So the picture is that you look at somehow. Okay, the disk has trivial fundamental group, so you cannot say that I want to get the sections of the fundamental group. But I want to have some kind of local systems on the disk, and these flags that we had before, they are sitting somehow on the boundary, along the boundary, and then the boundary itself corresponds to our restrictions. So there is this sigma I1, sigma I2 of the braid. So think about the disk, and then the braid is around on the boundary, and our combinations of flags are like somehow local systems on the disk. And then it turns out that by triangulating the disk and using these cocycles, we can construct some tautological, some classes, some differential forms, actually. Yeah? Differential forms on the braid variety. On that variety, which should give us the not in the so that's why we can ask, so from this philosophy, the Hovanov homology should have these interesting elements there. Okay, but the problem is that we didn't establish very well this correspondence between these varieties. We don't have general construction. So instead of sort of following our philosophy verbatim, we will just try to find these things in Hovanov homology. Just directly. So if you look toward these tautological classes, so I'm going to in the 𝔰𝔩2 triply graded homology. I want to switch to the second questions about it. So let's construct these classes. So how do you construct 𝔰𝔩2 triply graded homology? Recall that we have some ring R is polynomial ring. We consider R bimodules. And when you say bimodules, it means that there are two actions of R. So the modules variables and another calculator. So, and examples of such modules are itself such a bimodule where x primes act the same way as x, and another is the Poisson. This is given by but you identify J is not. We identify variables except one, but for I and a plus one, you only identify symmetric functions. Now, once you have these bimodules, you should think about it as somehow in my bimodule, and then there are x variables and prime variables, and then you can connect them by identifying. So you tensor the modules, but what it means, you just sort of put them together and identify the corresponding actions on the connections. So you tensor, we can tensor. Now, this is not the only thing you need to do. You have to also consider complexes. Also consider complexes. And then important is this 𝔰𝔩 complex is a complex where you send BI R, and it turns out that there is inverse, which is these are bimodule homomorphisms. And for each braid, you take the corresponding tensor product. So you take this product of sigma ik and corresponding f's, and it becomes this kind of hypercube, very big complex. And then this is called beta. And you, in the end, to get the invariant, you consider it's the quotient homology of this, and then you take you get a complex, and then you get cohomology of the complex. Wait. This is the triply graded. And what we want to do to find some extra structures here, so the main idea is to look for coincidences and make them part of the structure. So any coincidence be part of the structure. So one thing is an observation already used by earlier paper by Gorski and Hogenkamp, is that so the action in any complex f beta, the action of I homotopic to the action of xi. Okay, so if braid is pure, then this is true. If it's not pure, it's actually it should sort of permute the indices. But okay, just for simplicity, let's just say etc. I hope it's clear what I mean. So yeah, so how do you put it as a part of a structure? You say that, well, let's fix this homotopics. So let by psi I there's some element is that some map such that the boundary is different. Okay, so this was input. So what you actually do, you have to give explicit construction of this psi I, and that what they did, and that was input to the yification construction. But one thing turns out to be was not observed, and this is the second thing. Well, now notice that. So let f be a symmetric function. Symmetric. Then by the above f and is homotopic to f of the prime vectors, right? So each of them separately is homotopic, and you can prove that polynomials also for polynomials also true. But because it is symmetric, and if you remember the construction, all our modules are such that the action of any symmetric function on the left is the same as action on the right. So now we see that this is homotopic to this by this, and also it is equal. So they are equal in two different ways. So you can now take the difference, and then we can ask, is that homotopic to 0? And then the answer is, so is that thing, yeah. And if yes, then what can we construct explicitly that homotopic? And that's what it turns out to be true. So we can, so it turns out there exist some operations. Let's, I don't know, UF, which says that boundary of UF is the F minus F bar. So the difference of these two things. And now, okay, so we have this, this is the main idea. Now, how do we sort of formalize that? But we put it in the, we say that there is some, so when we say A infinity module, we actually mean DG algebra and DG algebra module. What is the infinity? So now let's so more generally. So we will have some. So if we have if you have DG differential graded algebra A, then we study A, and we call them infinity modules because so the modules, infinity modules are just modules, but the homomorphisms within them are different. Only so, but we do the following thing. But whenever we have homomorphism from some module M1 to M2, and such that it is a so this is so normally in this usual theory of infinity modules, you would say you would consider quasi-isomorphisms. Quasi-isomorphism is when is a homomorphism such that it induces identity. It induces isomorphism on the homology. But in this, we kind of have to extend our infinity definitions. So what extra thing is that in A we have some algebra B, and this B, okay, so such that it is a homotopy equivalent when now I will say what is A and B, but that's the general picture. You have an algebra, and inside there is some subalgebra. So first, the B is simply is a algebra generated by the modulo that any symmetric function in X equals to or any symmetric. This is our B, and all modules that we have seen, they are actually modules over B. Now what is A? And that's so the interesting thing. So A so A is this B, and then you add some more generators, and now these were all in homological degree 0, but now we have some other. So first we have the Wien size, and then we have this U. And so the algebra is just a polynomial algebra over A, so there's no relations, but all the interesting information is here in the differential. So I write the differential. So differential of size is also this is 0. And then differential of psi is xi. And differential of dk. So we have to work out this sort of idea for the case when f is a power sum function. So we use power sum. So what is this? This is a complete homogeneous symmetric function, the sum of all monomials of degree Q and so on. So you can clearly see that the square of the differential is 0, because if you apply the second time, you simply have to apply it to the sides. You get difference xi minus xi prime. And this will give you xi to the k minus xi prime to the k. So this is 0 in this algebra B. Yeah. So this is our infinity DG algebra. So I don't know if maybe I should point out that this algebra was slightly different version appeared before in papers by Abel and Hogenkamp, and so it is a resolution of R over D. It's a free resolution. In fact, is a resolution of R, the polynomials. So this sort of makes us think that maybe this is the best of possible algebra.
Sorry, when you say A is an infinity algebra, you mean that the higher structural maps are 0?
Yeah, it's just DG
Just the
algebra.
tradition of infinity.
It's just a DG algebra.
Okay.
But you know, it's known that any infinity algebra is equivalent to some DG algebra.
It's a minimum model which is given
Yeah.
by this DG algebra.
No, minimal model is when you cohomology, when differential is 0. It's not minimal model. Okay. It's something else.
Yeah.
Okay. Somehow resolution.
Yeah, and the infinity module is think of modules over this DG algebra that can have higher.
Yeah, so it turns out that, I didn't say that. So it turns out that, morphisms of infinity modules can have higher differentials. But what is true is that studying, if you localize, this I didn't say. I forgot. So if you localize by the class of these homomorphisms, you get equivalent. So we kind of encapsulate in algebra theory in this. Okay, so now let's continue the construction. So what about, for instance, F? So on I, which remember R, so the corresponding psi I minus 1 is a usual map from backwards, and so other 0, and use 0. So we have nothing interesting here in this case. But those interesting things start when you. So now, how do we define? So we want to define this action of this DG algebra on any f beta for any braid, and for that we have to define it on I's and then define how on tensor products. So now we have. So if we have 1, 2 are A modules, then in order to define two. So we somehow have to extend the IA action to the tensor product, and for that, then approach is to construct a coproduct on A. So we construct coproduct from A to A tensor where this tensor is over R, or like the same way as you tensor by moment. And that's given explicitly on generator. So for example, so here we denote xi prime and xi double prime, the generators. So the generators of A will be xi and xi prime. The generators of this A are xi prime and xi double prime. Then there are xi's. Here xi I and here xi prime. And the u's also here and here. And then we write some formula. So the I is simply xi. Is oh wait, sorry. I have to, it's this one. Then then the interesting part is U, and there is some nice choice too. Prime plus I H 2 and here we put so then you check that this is a DG algebra homomorphism, the differential preserved, and then we want to prove a theorem. So using these operations, we can define the A module structure on any of beta, and then theorem is that beta has a structure and of what? Of first presentation of beta, and then the choice you do when you tensor. So order tensor. So I have to now plan. I have to stop at 5 past. Okay. So I mean, once you have these things, the theorem, there is one tricky point in proving the theorem. For instance, proving that the coproduct is co-associative, which is important for the second part. And that this is some tricky thing. So you want to prove if when you apply this twice, you get two different maps to triple tensor product. And then, so I just, okay, so there's some issues. So for instance, if you have two homomorphisms between the algebras, and if they're simply homotopic, it's not sufficient to have, so that it's not enough to show that they use the same functors on modules. And then there is a little issue. Just a warning for you. It's not just checking that if you apply two twice, you get two homomorphisms. It's not sufficient to check that they are just homotopic. But there is some other condition that is sufficient. So anyway, so we prove this, and then we prove and then about the closure. Now we want to define a link invariant. So we have to close. Since we want to apply the Hofstad homology, so theorem 2. So if you take HH, this has A. So and so there is another infinite another DG algebra text here. There's an action of this algebra we call CA, which is basically the same as A, but I equals I. And again, it doesn't depend on the choices. So in other words, this module is a Lincoln range. Up to equivalence of the same thing. Okay. So there is this issue that somehow, if you take homology of this, you don't get any new interesting operations. It seems, or we don't know how to do it. So we have this DG algebra action, and the problem is that here you have this UK, and the D UK is still sum of K x I K minus 1. It's not closed. UK is not closed, so it doesn't define operation homology. And this still somehow mysterious. What can we get on the usual one homology? But if you verify, so there is this procedure of verification. It basically goes by taking of beta, entering with some polynomial extra variables, and you take mu differential, all differential plus some yi. And then you take the homology here. That has new operation, has interesting, has operations that looks as follows. They are they look like sum xi to the k d yi plus k. So there need this d, and this we call so they are independent of the choices. They are canonically operations and defined operations for any break, for any link. So commuting operations. Yeah. So this we call tautological class. Classes. And then, so what can we do with it? With an application, so there is completely different. So we look at the operator D2. Sorry, maybe so, the camera came on this one. We have this that looks like xi d over dy plus u2. And this we have this theorem for is that D2 is a part of SL2. Oh. EHF so yeah. And that's a corollary is that verified homology is symmetric with respect to changes xi and y. So there is involution. So this is sort of proof here is going by using Lefschetz theory. So there is a criterion when operator E is a part of SL2 triple. It has to do some isomorphism metric degrees. And here is interesting that so to prove it, we use some categorified scan relations, and each scan relation corresponds to a long exact sequence. And the thing is that this Lefschetz criterion is about some isomorphisms, being isomorphisms, and you can use 5 lemma for long exact sequences. So it's interesting, right? You cannot prove that some relations using long exact sequences, but you can prove that some things are isomorphisms. Yeah, and then so what did I forget to say? Yeah, so in the case of knots, the verified homology is not different from the usual homology. So you prove this conjecture for knots. Verified equals sort of very simply corresponds. It's just H with polynomials in one variable, and sort of you can eliminate x and y, and you obtain the proof that of this symmetry conjecture of Dunfield and Kukov and Rasmussen that if you take one of Rosansky homology of a knot, then there is some symmetry between certain bigradings. Yeah. And just the last piece just one minute. So there is this SL2 action, yeah, and there is this tautological classes. So you can, what is a sort of big algebra that they generate? And the suggestion is probably the algebra of X is on this Wi-Fi homology. So the biggest, maybe no. Okay, so big algebra. Maybe there is a big algebra on the Wi-Fi homology is the following. The Lie algebra of Hamiltonian vector fields. On C2, and explicitly it's given by operations of the form x to the. No, I will say it right. So this algebra has generators here, d over dy, x d over dy, y d over dy, and so on. In this direction, you have the d over dx, y d over dx. Well, there is an operation here. Do we have colors? Yeah. So this algebra, so the basis elements go in correspond to points here, and this is our SL2 that we talked about. But there is this sequence here, one step away from the boundary, is a positive part of the Witt algebra. It's probably that action constructed by Povanov. And it has another SL2 here, but it's different SL2. Yeah, and so that's, but we still don't know how to prove that all relations and the fact that but there are some ideas. So the fact that this is really that weird thing from home. Yeah, that's maybe the end of the talk.
Can you tell with this picture what is H? F you gave, but H.
Yeah, H. Sorry, yeah, H is which picture? This one?
Well, I mean, in your language, because I have an idea of what H should be, but
H is a Q degree. It's the degree that survives after you decriticalify.
multiplication by the Q degree.
The Wi-Fi homology, how many gradings? The Wi-Fi homology, as it's graded, how many gradings does it have?
Still 3. The 𝔰𝔩2, the polynomial grading, and the cohomological grading.
And so the degree of D2 is,
So you can look at here.
yeah,
It's like yeah, it's Q degree 2, which is supposed to be if it's part of the SL2 triple. Yeah.
does it have homological degree? I can't, I mean,
Yes, because Y is homological degree 2.
I think that's different than from Alana Brzezinski's wit actions. I don't think that acts.
Hold on. You don't take this. You take one step away. These operators look like
Oh, see, that would be the H in there. Okay.
x to the k minus 1 g over dx. I think minus yx to k, yx to the k minus 2, something like this.
Oh,
And if you kill y's, you get this.
I see. Hmm. Okay, let's thank Anton again.